Alright, so far we've been working with the disk method and the washer method. And the washer method is just if you revolve a figure around an axis or a line and you have some stuff missing, then it's basically you find the area of the entire figure with nothing missing, and then you subtract out that missing part. And so far, for example, let's say I wanted to revolve this in here about the X. The way that I've done that is I've thought about this like vertical rectangles, an infinite number of vertical rectangles, and I'm taking and revolving those about the X. And when you revolve a vertical rectangle about a horizontal line, then you're going to form a disk. Alright, and so you may or may not be missing some stuff inside. If you're missing stuff inside whenever you revolve, then it becomes a washer. But that's what we've been doing so far. Well, if we were to take, instead of using vertical rectangles, if we were to take and revolve horizontal rectangles, then when you revolve that horizontal rectangle around the x-axis, it would form a shell. So it would be like a cylinder. And each one of these rectangles that you revolve would form a cylinder. And you're saying, well, hey, you're missing stuff inside when you form a cylinder. But with the shell method, whenever you revolve an infinite number of these, it sums up all of that inside volume for you. Okay? And so the formula that we end up using for the volume of a shell is going to equal to the volume of the cylinder minus the volume of the hole inside. Alright, and so it ends up being, let's call the the volume of the cylinder once you simplify the formulas and put them all together, the volume of the cylinder minus the volume of the hole inside is going to end up being 2 pi times the average radius times the height times the thickness. Alright. And so the average radius, that's probably the part that students have the most problem with understanding. A lot of times it's the easiest thing though to write down. The average radius, let's say for all of these shells here that you make, the radius from the highest, or I guess the highest or the biggest, the tallest shell would be up here, and then the next shell, the next shell, the next shell, all of their heights here, or all of their radii will depend on where you are on the y-axis. So it's really just a function of y if you're going around a horizontal axis of revolution. So we say it's going to be some p of y, which if there's no space in between the axis that I'm revolving about and the actual, I guess the actual shells, there's no missing space, then most of the time this P of y is just going to be, if you're going about a horizontal line like this, it's just going to be x. So unless there's some missing space where you wouldn't have a shell, then it's just the variable x. Okay. The height of the shell is really going to depend on where you are, you know, like this side minus this side or something like that. So the height we will have to figure out, and it's going to be represented by some h of y if we're going about a horizontal axis. And then the thickness here, that's going to be our dy. Just like the thickness for any of the rectangles when we were forming discs or washers, the thickness was the dx. And so we have two formulas just like we do for the disc or washer method, depending on whether you have a horizontal axis of revolution or vertical axis of revolution. So if we have a horizontal axis of revolution like we did above when I was showing you, then my formula for volume is 2 pi times the integral from c to d. The c and the d, that's usually associated with y boundaries. So those will come usually from the y-axis of p of y times h of y dy. Remember, p of y is the average radius, h of y is the height of each one of the rectangles, and the dy is the thickness of the rectangles. Okay? So remember that with the disk and the shell method, if you have a horizontal axis of revolution, you want y equals x. It's just the opposite with the shell method. If you have a horizontal axis of revolution, you want x equals y. All right, and so for a vertical axis of revolution, volume is equal to 2 pi times the integral from a to b of p of x times h of x dx. The a and the b, that's usually associated with x boundaries. All right, and then of course this is p of x, that's going to be like a y equals x. So most of the time, unless there's some missing space, most of the time that's just going to be y. All right, and the height, that's going to be some y equals x, some formula that we have to come up with depending on what the functions are. And then the dx, that's going to be the thickness of each one of our shells. Okay, so the biggest difference between the shell method and the disk method is that you set them up, I guess if you think y equals x and x equals y is setting them up the opposite way, you set them up the opposite way, and instead of just having a pi in front, you have a 2 pi in front. And that's just because of the way that the formula simplifies whenever you come up and derive the formula for the shell method. That 2, in the disk method, it ends up canceling out and you don't have to worry about it. With the shell method, we have 2 pi in front. Okay, so let's look at an example of the shell method. So let's find the volume of the solid of revolution formed by revolving the region bounded by y equals x minus x cubed about the x-axis bounded by, let's see, bounded by y equals x minus x cubed and, not about, but and the x-axis, x is greater than or equal to 0, less than or equal to 1, about the y-axis. This will make a little bit more sense, all of these boundaries will, when we actually look at the figure. Alright, so what we have to do is first give it a rough sketch of the figure. So first we have to know how to graph this. This is a cubic if you were to graph it out completely, because you have x to the third power as the highest power. Now I would suggest that you try to figure out the x and y intercepts, or you make a really good table whenever you graph this, or you use a little cal1 and find critical numbers and do all of that. Okay, concavity, you can do as much as you want. But you sketch this right here. I usually if it's not a very complicated graph, you can just use x and y intercepts. So my x-intercepts, you set y equal to 0 and solve. So if I say x minus x cubed equals 0, to solve for x, you'd want a factor. That would be x times x, no, so x times 1 minus x squared. And then once you have a product here, you can set each one of those equal to 0. So we know we're going to cross at x equals 0. And then if I move my x squared over, I would have x squared equals 1 if I flipped it around. So I know that this graph will also cross at x equals plus or minus 1. So we know we're going to touch the x-axis in those three places. Then I would figure out the y-intercepts. So for the y-intercepts, you set x equal to 0. So I just have y equals 0 minus 0 is 0. So that means we're going to cross here. That's the x and the y-intercept. And then we know we're going to cross here at x equals 1. And you're going to cross here at x equals negative 1. Okay. You could then use the first derivative test or anything else you want to use to find other points. You could make a table and figure out points. It's really up to you. But you would figure out that this graph would basically look something like this. So it's going to be going down through this point, it would be going up through this point. And that's the basic shape of a cubic graph. It's an N-shaped graph. And since the cubed is negative, that's why it's kind of a, I guess, a backward N-shaped graph. Anyway, what are we concerned with? It said that it's bounded by this graph and the x-axis, where x is between 0 and 1. So here's where x equals 0. here's where x equals 1. So we're just concerned with this part here. Alright? So what we're going to do is we're going to take vertical rectangles and we're going to revolve them about the y-axis. And here's the y-axis right here. So we're going to be forming cylindrical shells. If you thought about revolving about the x-axis, well, think if you revolve about the x-axis, you would be making discs when you revolve. That would be the disc method. So this is using the shell method. So we're revolving these shells about each one about the y-axis. Okay. Alright, so we now need to figure out the formula for the volume. Since we have a vertical axis of revolution, we want all of our functions to be y equals x. Alright, I'm going to write down the general formula that we use. It's 2 pi times the integral from c to d of the average radius times the height dx. Alright, so let's figure out the formula that we use. Volume equals 2 pi times the integral. Alright, remember c to d, that means that we want to use y points. So we are going to have to know where this highest y point is. The easiest way to figure that out would probably be by using the first derivative test. That high point is going to be a place where you change from increasing to decreasing, or at least look at the critical number. So if we took this function right here and we took the first derivative, we would have 1 minus 3x squared. And if you set the first derivative equal to 0, what does that do? That gives you all the critical numbers. So you'd have 3x squared equals 1. If you move this over and flipped it around, you divide both sides by 3. And so you have x squared equals 1/3. When you move that over, it becomes positive. And then you flip it around, all this would be positive. So divide by 3 on both sides, take the square root of both sides. So x equals plus or minus the square root of 3. The square root of 1/3, which is plus or minus the square root of 1 over the square root of 3, which is plus or minus, rationalize, and you have square root of 3 over 3. So what this tells you is you have a high point and a low point, more than likely. These are the two critical numbers, at positive square root of 3 over 3 on the x and negative square root of 3 over 3 on the x. So if I had to guess, right here, that's going to be an x value of positive square root of 3 over 3. And right here, that's going to be a negative x value of square root of 3 over 3. We don't need x values to set up our integral. We need, yes, do we need x values or do we need y values? I was looking at this right here when I wrote this down. I think this is from A to B, not from C to D. Look back at your formula. I wrote down C to D. That's if you have x equals y. So I just did a lot of work for nothing, really, because I don't need the y values. Even though they will help me maybe figure out if I'm setting my equation up right. I only need the x value, so this was a little bit easier than what I made it look like. So don't set it up using y values. if we use x values, then what would I use? 0 to 1. So 0 to 1. I told you that the average radius, most of the time you're just going to use x or just use y. So if I want p of x, that's the average radius. This is set up y equals x because p of x is the same thing as y. So whenever I set this part up, all I do is write an x. Alright, times, now this is the height of each one of these rectangles. So the height is going to be, you know, wherever you are here on the y, that's the height. So it's going to depend on this curve right here, right? The height depends on where you are on this curve. So the height is just going to be the equation for this curve right here. And that's x minus x cubed. We can check those heights if we want to. If we plug in a 0 for this height right here, I should have a 0 height. If I plug in a 1, what should the height be? It should be 0. 1 minus 1 cubed. 0. We could plug in a square root of 3 over 3 if we wanted to and figure out the height right there. That would require a little bit more work. But just looking at it, at this on the left side and on the right side, we have a height of 0, and that works out in our formula. So we have it set up right. Okay? So then we just have dx. So now this integral is pretty easy, right? It's 2 pi times the integral of, you'd probably want to just multiply that in. That'd be x squared minus x to the 4th. And integrate that. So it's 2 pi times, that's going to be x cubed over 3 minus x to the 5th over 5. And that's from 0 to 1. Alright, so that's 2 pi times, plug in the 1, that'll be 1/3 minus 1/5, minus, plug in the 0. When I plug in the 0, I'd have 0 minus 0, or 0. Alright, so that's 2 pi times a third minus a 5th. Common denominator is 15. 3 going to 15 5 times. 5 times 1 is 5. 5 going to 15 3 times. 3 times negative 1 is negative 3. So it's going to be that's going to be a positive 2/5. Or I'm sorry, 2/15. So 2 pi times 2/15 is what? 4 pi over 15. So the volume for that figure, if it was revolved about the y-axis, would be 4 pi over 15. Now let's look at this problem here. Let's say that we have y equals 1 minus x. Y equals 0, x equals 0, and we want to revolve that bounded region about the y-axis. Alright, so first we need to graph y equals 1 minus x. Since that is a linear equation, you can see that the slope of the line is going to be -1 and the y-intercept is going to be +1. You could use that Or you can use the X and Y intercepts like we used on the last problem. If we use the X and Y intercepts, the X-intercept is going to be, you let Y equal 0, so it's going to be a positive 1. The Y-intercept, if you let X equal 0, is going to be a positive 1. So I'm saying that's positive 1x, that's positive 1y. So this line right here, that's y equals 1 minus x. And then y equals 0, you go right here where y equals 0, and you draw a horizontal line. X equals 0. You go right here where x equals 0, and you draw a vertical line. Alright, so I am revolving this region in here about the y-axis. So right here, right around here. So I'm taking vertical triangles, these vertical triangles, and I'm revolving them about the y, and that's going to form a bunch of shells. Okay. So let's set this thing up. The volume equals, since we have a vertical axis of revolution, that means that we want y equals x. So volume equals 2 pi times the integral of, now we want to integrate this from A to B. Since it's a vertical axis of revolution, we want to use x values. So we need this x value, and we need this x value. So this is the integral from 0 to 1. Alright, now remember what goes inside here. The average radius, which the average radius is the average radius of each one of these shells. The radius is going to depend on where you are on the x-axis. It's going to be anything between 0 and 1, but we can just say the average radius is x. Now the height of each one of these, this height, is going to depend on this curve right here, this line. Alright, so it depends on where you are on the line as to the height. So it's just this equation here. It's 1 minus x. The thickness of each one of those shells that I'm creating, that's the dx. Alright, so that is 2 pi times the integral of x minus x squared. So that's 2 pi times, that's going to be x squared over 2 minus x cubed over 3, evaluated from 0 to 1. So that's 2 pi times, when you plug in a 1, you'll have 1/2 minus 1/3. Minus, when you plug in a 0, you get 0 minus 0. So that's just 0. Alright, so this is 2 pi times, what's 1/2 minus 1/3? 1/6. So that's 2 pi over 6, or pi over 3. That's the volume, pi over 3 cubic units. Alright, let's look at another one. Let's say we have y equals 1/2 x cubed, y equals 0, x equals 3, and want to revolve that about the y-axis. Alright, so if we use the x and y intercept to graph this, keep in mind this is a cubic, so it is going to be kind of N-shaped. It's going to be an N-shaped graph. You may want to graph a couple of points to get a good picture of this. I'm going to go ahead and mark off my x-axis a little bit so I can plug in a couple of x values. But because I see that if I plug in, if I want to find the x-intercepts and I let y equal 0, that's just going to be 0. And if I find the y-intercepts by plugging in x equals 0, that's going to be 0. So this is the only place that it's going to cross the x-axis. Alright, so you may want to plug in a couple of values to get a better picture of it. So if I plug in a 1 on the x, I'm only at 1/2 on the y. And if I plug in a -1 on the x, I'm at -1/2 on the y. If I plug in a 2, though, you can see this thing it increases pretty fast, because that's going to be 8 divided by 2, or 4. And if you plug in a -2, that's going to be a -4. Alright, so this graph is going to kind of look like this. Alright, and it's kind of an N-shaped graph that's stretched out a little bit. Alright, then I have y equals 0. So y equals 0 is the x-axis. Alright, and then I have x equals 3. So the way that my graph is drawn is probably not to the best scale. You can see that's a big 1 right there. So this graph, I'm going to have to extend it out a little bit. I'm going to have to extend that out a little bit. So here's x equals 3 right here. And so what I'm doing is I'm taking this region in here, all of this. I'm going to form some vertical rectangles in here and revolve them about the y-axis. Okay. Alright, so the volume is going to equal 2 pi. Believe it or not, a lot of students forget the 2 pi with the shell method. They get the two formulas confused and they'll just put a pi in front. It's not going to be right if you just put pi. So times the integral. Now we use x boundaries. 0 to what? 3. The average radius is going to depend on where you are on the x-axis. The radius is going to depend on where you are on the x-axis. So the average radius is just going to be x times the height of each one of these rectangles that's being formed. That's going to depend on this curve here. That would give you the height at any point. So the curve is 1/2 x cubed. The thickness of each one of the shells that I'm going to form is dx. So volume is 2 pi times the integral of, that's just going to be 1/2 x to the 4th dx. So that's 2 pi times, I'm going to go ahead and bring out the 1/2. If I bring out the 1/2, you can see that cancels out. And I'm just integrating x to the 4th. So that's x to the 5th over 5, evaluated from 0 to 3. So that's going to be pi times, plug in a 3 to the 5th power, that's a pretty big number. So 3, let's see, x to the y is somewhere, x to the y 5, so 243 over 5. Plug in the 0, get minus 0. So it's 243 pi over 5 is your volume. Alright, so let's say that we wanted to take the region bounded by these graphs and let's revolve them about the line x equals 2. So about x equals 2. Alright, so the in-shape graph, I mean, you can figure out the x-intercepts and the y-intercepts by letting y equal 0 and x equal 0. If you let x equal 0 to find the y-intercepts, y equals 1, so we know it's going to cross at y equals 1. Let's say that's right here. If you let y equal 0 to find the x-intercepts, that's a little bit more complicated, so either you would need to use some type of technology to do that, or you'd have to get really lucky with some x and y values. But you can see that as x gets bigger here, as x gets larger, the y is going to get larger. So what that means is even if x is 0, we know that it crosses here. Well, if x goes up by 1, that's going to be a bigger number. If x goes up to 2, that's going to be a bigger number. So it's never going to cross the x-axis over here. All right? It's just going to get bigger and bigger and bigger. It's not going to be a U-shaped graph. It probably, you know, I'm just going to give a rough guess here. It probably goes down something like that. But you don't need that side, so it really doesn't matter. You just need the right side because of these other equations. All right, so y equals 1. We go to where y equals 1, that was right here, and draw a horizontal line. X equals 1. Well, let's say x equals 1 about right here. I'm going to put x equals 2 about right here. Here's x equals 1 here. And then x equals 2 is right here. Alright, so the bounded region is going to be this region in here. So we want to take this region in here and we're wanting to revolve it about x equals 2. And remember, this line is x equals 2, this vertical line. So with a vertical axis of revolution, we still want y equals x. It's good, that's the way our equations already are. So I'm going to be making vertical, I'm going to use vertical rectangles, and I'm going to revolve those about this line. So I'm just going to kind of give you a rough sketch of what that would look like. You'd have, you know, let's see, it's got to be that distance plus a little bit more. So let's go over just a little bit more. You know, so I would be making shells. That's just what one of those shells would look like, something like that, if we could see through the front of it. Okay? Now, remember, the radius that we come up with for this particular one is going to have to be from this on the x all the way to the center. So we need to be able to get that whenever we plug in our equation. If I was just to use the x as my radius, just this x value, then I would just get this distance right here. So whatever x that is, if I just use that value, I'm going to get that distance for my radius, and that's not right. We want to say, how many units was it out here to the center? 2. That's the line, x equals 2. We want to say 2 minus whatever x we're at, and that will give you the distance here. So the average radius, the p of x, is 2 minus x. That will give me the distance from here to here, saying 2 minus x. Alright, the height of each rectangle, h of x. Alright, the bottom of the rectangle is not y equals 0, is it? The bottom of each rectangle is y equals what? 1. Everybody see that? This, because remember we bound this thing by y equals 1. So before, on our previous problem, or 2 problems ago, I told you the height is kind of like just this line. I guess it was the previous one. No, it was this one. Was this line minus y equals 0, even though we don't say that in the problem. That's how you get the height, the top curve minus the bottom curve. We have to do the same thing here because we're missing a space, we're missing a piece right here. You're missing all of this. So you have to say the top curve, whatever curve this is, minus the bottom curve. That's going to give you the height, the top minus the bottom. So the top curve was x cubed plus x plus 1. The bottom curve here was y equals 1. So you have to subtract that 1. So your height is going to be x cubed plus x plus 1 minus 1. So just x cubed plus x is going to be your height. Alright, and so to find the volume, this is 2 pi times the integral of, now we're using x values, alright, so look at the shaded region and what are its x values. Here's the shaded region here. What are the x values? 0 to 1, same as before. It's not 0 to 2. If I go 0 to 2, then I'm including all this stuff in here. It's just 0 to 1. Alright, and then my average radius is 2 minus x. That's how you get the radius at any point. You have to say the fixed value of 2 minus whichever x you're at, times the height of each one of the rectangles. The height is x cubed plus x. And then the width of each one of those rectangles is dx. So we need to FOIL this out. So that's 2 pi times the integral from 0 to 1 of, FOIL this out, that's 2x cubed plus 2x minus x to the 4th minus x squared dx. I don't see any like terms. You might want to go ahead and just arrange those from biggest power to smallest power. I'll do it one more time and arrange those from largest to smallest power. So that'll be negative x to the 4th plus 2x cubed minus x squared plus 2x dx. And that's from 0 to 1. So 2 pi times, that's negative x to the 5th over 5 plus 2x to the 4th over 4 minus x to the 3rd over 3 plus, that's 2x squared over 2. So you can see that cancels out there. Right there, that cancels out and gives me 1/2. And I'm evaluating from 0 to 1. Alright, so that's 2 pi times, plug in a 1, that's going to be negative 1/5 plus 1/2 minus 1/3 plus 1 minus, and when I plug in a 0, I'll get 0, 0, 0, 0. So minus 0. Alright, so that's going to be 2 pi times, got to get a common denominator. Looks like that common denominator could be 30. So that would be negative 6 plus 15 minus 10 plus what? 30. Alright, so that's 45 minus 16 too big for me to calculate in my head, even though it's not very big at all. Alright, 29 over 30. You gotta say 2 pi times that, so that would cancel out. We get 29 pi over 15 as our volume. So with the shell method, you don't have to do anything with the average radius as long as you're revolving about the y or about the x. But if you're revolving about something that's not one of the axes, then you have to be careful and make sure that you adjust. So this problem, we're revolving about x equals 2. So to get the radius of any rectangle that I revolve, I have to say the 2 minus whatever x I'm at, and that will give me the radius. Alright? So as long as you're just revolving about the x or about the y, you're not going to have to do that. Also, the height, make sure that your height of each rectangle is bound top minus the bottom. If this would have went all the way to the x-axis, then it would just be the top minus 0, but it didn't. It just went to y equals 1. So if say the top curve, which is y equals x cubed plus x plus 1, minus the bottom curve, and the bottom curve was 1. So that's why I had to say minus 1 so that I could get the height of each rectangle.